and today we're going to go on to section 13.4, which deals with the cross product. Last time we did the dot product, or the scalar product, and that enabled us taking the dot product of two vectors to get a scalar. Today we're going to go on to the cross product, and what the cross product is going to give us is, when we take the cross product of two vectors, we're going to get a vector. So first of all, let's look at what is the definition of the cross product of two vectors. I have it down here, and let's look. If vector A is defined to be A1, A2, A3. In fact, people don't copy this down frantically because I'm going to show you a better way to remember it. But if the formal definition is if vector A is A1, A2, A3, and vector B is B1, B2, B3, then the cross product of A and B is the vector, which we denote as A cross B, and it has an X, a Y, and a Z component. Notice the X component, you're sitting there and you're looking at it like, my goodness, how am I ever going to remember this? But don't worry about it. It's A2B3 minus A3B2 times I. The Y component is A3B1 minus A1B3 times J. And the Z component is A1B2 minus A2B1 times K. Now remember, last time when we did A dot B, we got A1, B1 plus A2, B2 plus A3, B3, and that gave us a real number. The dot product of two vectors gave you a number like 2 or 5 or 6 or 8 or 12 or 0, right? Where the cross product gives you a vector. A cross B gives you a vector. It gives you a three-dimensional quantity. Now let's go on. To help you, you're looking at this and I'm sure you're thinking like, wow, how am I going to memorize that formula? You know, I'm going to definitely have to put this on my cheat sheet because there's no way I'm going to remember it. Instead, I want to give you a way that you can remember it so that you don't always have to be looking at your cheat sheet. You might remember, I think some of you did this in intermediate algebra here at Del Tech, or I even think this is covered in the 182 course. If I write straight line A, B, C, D, this is known as a determinant. We've had determinants before. And to evaluate this determinant that's written this way, you start in the top left-hand corner and you take A times D and then subtract B times C. So you always start in the left-hand corner and take this times its diagonal minus the product of the other diagonal. So if you wanted to, like maybe you had 2, 3, 4, and 5 here, and you wanted to evaluate that determinant, you'd start with the 2 and you take 2 times 5 minus 3 times 4, which would give you 10 minus 12, which in this case is a negative 2. Now right now you're thinking, what does that have to do with that cross product that she was talking about? All right, we also have a three-dimensional 3 by 3 determinant. Now some of you have had determinants, others have not. To evaluate this determinant, what we do is we're going to go across the top row. All right, so first we're going to take A1 and we're going to multiply it times, and we're going to eliminate the row and the column that A1 is in. So we're going to eliminate this column and we're going to eliminate this row, and what we're left with is B2, B3, C2, C3. Okay, so it's A1 and you eliminate the row and column A1 is in, and you multiply it by the determinant of what's left, that B2, B3, C2, C3. Then we go to A2. Now it always goes positive, negative, positive. So for A2 we write minus A2 times, and it's going to be the determinant of the row and the column that we eliminate that A2 is in. So we eliminate A2, its row and its column, and notice what we have, B1, B3, C1, C3. And the next one is plus A3 times, and that determinant is going to be eliminate the row and the column that A3 is in, which gives me B1, B2, C1, C2. Okay, and that's how you will evaluate a 3 by 3 determinant. Now right now you're thinking, what does that have to do with the cross product? It has a lot to do with the cross product. All right, because when I want to take the cross product of vectors A cross B, I write determinant. Across the top I put I, J, and K, the unit vectors I, J, and K, and then I put vectors A's components for the second row and vectors B's components for the third row. And evaluating this determinant, look what I get here. I get the first, I'm going across the top row, so it's going to be I times the determinant that I get when I eliminate the row and column that I is in. So that gives me A2, A3, B2, B3. Then with J, we go minus J times the determinant that we get if we eliminate the row and the column that J is in. So that gives me A1, A3, B1, B3. Plus K times the row and column that K is in, which gives me A1, A2, B1, B2. And if we evaluate each of these determinants, look what I get here. I times, this is going to be A2, B3 minus A3, B2 minus J times, now this determinant is going to be A1, A3, excuse me, A1, B3 minus A3, B1 plus K times A1, B2 minus A2, B1. Now let's pull back that formal definition that I gave you at the beginning of the period, which was right here. Okay, notice A2B3 minus A3B2. Now notice here I have, it's flip-flopped, but we have a minus in front of here. And if we distributed this minus sign, we'd have minus A1B3 plus A3B1, which is exactly what we had in the formal definition. Plus, and for K, its component was A1B2 minus A2B1. So that determinant is a really nice crutch to be able to evaluate the cross product of two vectors. So without further ado, let's practice. First one that I want to practice is, I have vector A being 1, 3, 4, and vector B being 2, 7, negative 5, and I want to evaluate their cross product. So I'm going to put I, J, K across the top. Then I put A's components, 1, 3, 4, and B's 2, 7, negative 5. Okay, let's move this up a little bit. And to evaluate that determinant, what I need to do here now is, this cross product is going to equal I times the determinant that I get when I eliminate the row and the column that I is in. So that gives me 3, 4, 7, negative 5. Minus, don't forget that minus. Let's put it in red for you, in fact. Minus J. And then we eliminate the row and column that J is in. That gives me 1. Notice when I eliminate that column, I get 1, 4, 2, negative 5. Plus K times, eliminate the row and column that K is in. That gives me 1, 3, 2, 7. Now I have to evaluate each of those determinants separately. So this equals I times, and notice we start in the top left-hand corner and go this way minus this way. So it's 3 times a negative 5, which is a negative 15, minus 7 times 4, which is 28, which looks like, let's see, minus 43i. All right, this is minus J times, I'll make parentheses here. Again, we start in the top left-hand corner and we go down, minus, go the other way. So 1 times a negative 5 is a negative 5, minus 2 times 4 is 8. So this is a negative 13, but since it's a minus here, it'd be plus 13J. Plus K, again, we start in the top left-hand corner and go this times this. 1 times 7 is 7, minus 3 times 2 is 6. So that gives me plus 1K or K. And so the dot product is this vector, the vector minus 43i plus 13j plus k. Okay? Now right now I'm certain, and I wrote it down here to make sure that I have the right answer, and I do. That's good. All right? I'm certain most of you are sitting there thinking, why? Ms. Strocko, why does anybody care? Okay? Why would anybody, I mean, right now what we have is we have the cross product of two vectors produces a vector. But what do you care about that vector? What's important? What does it do for us? All right? Well, first of all, I want us to note that if you take A and dot it with its cross product. And don't frantically write this down right now. Just sit back and invite the show, because you copy, 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 and then you miss what's going on. I want to verify that if I take the dot product of A with A cross B, or the dot product of B with A cross B, I'm going to get 0. All right, now, why is that important? Why do I care about going on to that? Do you remember when we did the dot product? You know, you had two ways of doing the dot product. One way was, you know, we had A equal to the vector A1, A2, A3, and vector B was the vector B1, B2, B3. And the first way we defined A dot B was that, you know, you multiply the x coordinates together, plus multiply the b coordinates together, plus multiply the c coordinates together, and that was all well and good. But what was the other way that you did that you could take A dot B? Remember what the other definition was? It was the length of A times the length of B times the cosine of the angle between them. Well, what if this turns out to be 0? Since the length of A is not 0, the length of B is not 0, the cosine of the angle has to be 0. And the cosine of what kind of angles are 0? 90, 270, right? 90, 270. Well, gee, the angle between them is 90. It looks like this. If it's 270, I guess you're just measuring it this way instead. Either way, they are perpendicular to each other. By the way, from grade school, you use the word perpendicular. What word does your book like to use? Orthogonal. So when you see orthogonal, two vectors are orthogonal, it also means they're perpendicular. And later today, or it might not be today, but later on, you're going to also see me use the word normal, saying a vector is normal to a plane or something. That also means it's perpendicular. So these three words all mean the same thing. Okay, so coming back here, the reason I want to verify that A dotted with A cross B is 0 is when the dot product of two vectors is 0, it means that these two vectors are perpendicular to each other. So in a minute, I'm going to verify that A dotted with A cross B is 0 and that B dotted with A cross B is 0. And the reason I care about that is this cross product is giving me a vector that is perpendicular to each of the other two vectors. So when you take the cross product of two vectors, you're getting a vector. So if you have a vector here and a vector here, the cross product is going to be perpendicular to those two vectors. And there's going to be times where we're going to want to generate a vector perpendicular to two other vectors. Now, as you realize, there's infinitely many vectors that are perpendicular to those two vectors, because if you get one that's perpendicular to both of those, you can double them, you can triple them, you can multiply them by a -1, and all of those are still going to be making a 90-degree angle. So in a few minutes, we'll have to figure out, well, what else do I know about this cross product vector that makes it so special? Now, don't copy this down, just follow. First of all, I'm defining A to be A1, A2, A3, B to be B1, B2, B3. And A cross B, this is the definition that we had. You don't need to copy it down. All right? But I'm just reviewing that. All right, now, if I wanted to take A cross B, let's look. If I wanted to take A and dot it with A cross B, all right, you with me? A, this is A, which is A1, A2, A3. Here's its x coordinates, times A cross B's x coordinate, y coordinate, z coordinate. This is just plugging in for A, A1, A2, A3, and for A cross B, this. And when we take the dot product, we take this x coordinate times that x coordinate, that y coordinate times that y coordinate, that z coordinate times that z coordinate. Since they're vectors, I really should call them components. And this is the mess I get. If I multiply that out, which I took the time to do, I get that. And lo and behold, look what happens here. I have an A1, A2, B3, and I'm subtracting, let's see, here, in fact, let's look here. We have A1, A2, B3, and here we have, let's look for the other, here, A1, A2, B3. They cancel each other. And here I have an A2, B1, A3, and here we have a A2, B1, A3. One's a plus, one's a minus. This one here is A1, A3, B2. They cancel each other. And if everything cancels, what do we end up with? 0. So we just proved that A dotted with A cross B is equal to 0, which implies that when the dot product of two vectors is 0, it means the one vector is perpendicular to the other. On the flip side, if we did the exact same thing, which we will in a second, with B dotted with A cross B, again, B's components are B1, B2, B3, and they get multiplied times A cross B's components. Here's its X, here's its Y, here's its Z. If I multiply that out, and I'm not going to be as dutiful as showing what cancels, it's all going to cancel out, and I get 0, which implies that B is orthogonal or perpendicular to A cross B. So when you take the cross product of two vectors, you are producing a vector that is perpendicular to each of those two original vectors. That's a powerful tool, real powerful. So in summary, A cross B is a vector that is perpendicular to both A and B. Okay, that's an important thing. Now, this theorem is on page 852. I toyed with the idea of going through the whole proof, and then I decided, you know what, we already did that one proof. It's a bit tedious. If you really would like to read the proof, they have a lovely, they have it all written out, and it's on page 852. All right, but we're just going to take it at face value. And look what this tells me. A cross B gives you a vector. All right, here's A. Let's say here's B. And we're saying theta is the angle between the two vectors. It could look like that, or, it's saying the angle has to be between 0 and pi. So you could have like A here and B here, in which case the angle is going to be bigger than pi over 2. Okay, it's going to be an obtuse angle. What this theorem says is the magnitude of A cross B is equal to the magnitude of A times the magnitude of B times the sine of the angle. Okay, so what do we have so far? When you take the dot product, that gives you a number. And that number is equal to the length of A times the length of B times the cosine of the angle between them. A cross B is not a number. It is a vector. If we're in three-dimensional space, it will have an X, a Y, and a Z component. But if you take the magnitude of that vector, how long is that vector? It is equal to the length or the magnitude of vector A times the length or the magnitude of vector B times the sine of the angle between them. And that angle has to be between 0 and pi, or 0 and 180. So if it looks like this, you're not going to go like that. You're going to take the acute angle. Okay? Piece of cake. And by the way, and the proof is delightful what they do. They take A cross B and dot it with A cross B, but we're not going to go through that. I just want to spend time what we can do with this. All right. One more thing I want to go over. Suppose vector A is parallel to vector B. Suppose vector A is parallel to vector B. What does that mean for two vectors to be parallel? That means the one vector looks like this, and the other vector might look like, okay, they're parallel. Now remember, if I want to find the angle between them, what is the angle between them? Remember, you can always draw a vector it has the exact same direction and the same length, but move the two vectors tail to tail, right? So if I move this vector B to be tail to tail with vector A, what is the angle between them? 0. Now we could also have another vector. Let's do this one. I could have another vector that goes this way. And if we'll call him A1, and if I slid him, what's the angle between those two vectors? 180, right? For either of them, if I have vector A and vector B parallel, the angle between them is 0 degrees or 180 degrees, right? So the magnitude of A cross B will equal the magnitude of A times the magnitude of B times the sine of the angle between them. But people, what is the sine of 0 degrees? 0. What's the sine of 180 degrees? 0. So this number right here is a big old fat 0. And so the magnitude, the length of vector A cross B is going to be 0. Well, what vector has its length equal to 0? The 0 vector. That tells me A cross B has to be the 0 vector. In other words, the vector whose components are 0, 0, 0. So what we have just proven is if two vectors are parallel, their cross product will give you the 0 vector. So I have that in summary right here. If two non-zero vectors, A cross B, are parallel, if and only if their cross product is equal to 0. So notice, we might want to write this down. If you have two vectors A and B, and notice when you take the dot product, you get a number. So I don't put an arrow over it, it's just a plain old everyday number. When the dot product was 0, what did that tell you about your vectors? That told you that A was perpendicular to B, right? When your dot product was 0, your two vectors were perpendicular. What we have just proven is, now remember, cross product gives you a vector. So it doesn't give me the number 0, it gives me the vector 0 that has an x, a y, and a z component of 0, 0, 0. When your cross product is 0, that means A is parallel to B. So when the dot product is 0, you have perpendicular vectors. When the cross product is 0, you have parallel vectors. So it's a nice way to be able to check out parallel and perpendicular. By the way, if you give me two vectors and you ask if they're parallel, I just use the fact that two vectors are parallel if you can multiply the one by a scalar to get the other one. Okay, just in summary, let's look at this. Let's look at vector A, and let's have its components be 1, 2, 3. Suppose I had vector B, and its components are 3, 6, 9. Are those vectors parallel? How can you tell if they're parallel? Remember, you're parallel if you can multiply the one by a scalar to get the other, because you can stretch the one to get to the other. Well, if I take vector A, what do I have to multiply it by to get vector B? 3, sure. If you take vector A and multiply it by 3, you get 3, 6, 9. So therefore, if I stretch this vector, I get that vector. They are parallel. So the definition of parallel is if you take one vector and you can multiply it by a scalar to get the other, then that implies that A is parallel to B. But we just said if they're parallel, their cross product should be 0. Let's see if that's the case. Here I have vector A was 1, 2, 3, and vector B is 3, 6, 9. Let's take A cross B. So I go I, J, K, and for A I'm going to put 1, 2, 3, and for B I'm going to put 3, 6, 9. And this will give me I times, eliminate the row and column that I is in, and I'm going to get 2 times 9, which is 18, minus 6 times 3, which is 18. Look at that. That gives me 0I minus J. We eliminate the row and column that J is in, and we're going to have 1 times 9, which is 9, minus 3 times 3, which is 9. 9 minus 9, which is minus 0J, which I could write as plus 0J. Plus K times, let's eliminate the row and column that K is in. 1 times 6 is 6, minus 2 times 3 is 6. 6 minus 6 gives us 0K. So what do we have? We have the vector whose x, y, and z components are 0, 0, 0, which we write like that. So we just verified. We have two vectors that we just showed were parallel, and we just showed that their cross product indeed is 0. Okay, not hard. Not hard. Okay, moving right along. In summary, two important things to know. A cross B is a vector. It is a vector. It's a three-dimensional quantity that's perpendicular to both A and B. And we did not prove this, but I told you where you can go in the book to read the proof. A cross B, this means the magnitude. The length of A cross B is equal to the magnitude of A times the magnitude of B times the sine of the angle between them. All right. One other thing. Notice if I have two vectors, if I had like this vector and this vector, this is a little red vector, this is a little blue vector, and I wanted to figure out what direction is my vector going that's perpendicular. Notice you could have your vector coming out like this, pointing up that way, but you also could have the vector pointing down like that. So you want to, gee, when I do A cross B, which way does it go? Is it going up or is it going down? And I'm not going to prove this, but we have something called the right-hand rule that says if you take I'm not going to write out the rule, I'm just going to do it verbally. If you take A cross B, like in this particular case, let's pretend the red vector is A, and let's say the blue vector is B. What the right-hand rule says, if you want to take A cross B, you take your right hand, take your palm, the bottom of my hand right here, put it where A is, and rotate it towards B, and my thumb is pointing up in the direction that A cross B is going to be pointing up. Any of you guys that are taking physics, you know, you're going to be doing do magnetism, you're going to find that whole thing about the cross product. But this is A cross B, so this vector would be pointing up. Now notice if I wanted to take blue cross red, I can't put my hand this way to go this way because I got to rotate it towards. You follow? So I got to take my hand down and go red to blue, and notice which way is my thumb pointing? It's pointing down, so blue cross red would be pointing down. And that's called the right-hand rule in terms of figuring out which way that vector is doing. Now also, I'm thinking this A cross B equals magnitude of A times magnitude of B times the sine of the angle between them. I'm thinking, what geometric significance does this magnitude of A, magnitude of B times the sine of the angle have? All right, we now know the vector is perpendicular to both, and we know the right-hand rule we can use, but what does this do for us? So one more thing. Oh, no, I don't want to. Oh, we'll do that one in a second. Oh, maybe I'll do these now, and then I'll go back to significance. Notice, now we'll go over these real quick. A cross B is equal to the opposite of B cross A, because notice we said if we go red cross blue, my finger's pointing up this way. But if I took blue cross red, I'd be going that way. So the vectors, one would be pointing straight up, the other would be pointing straight down. So they're in opposite directions. So that's a nice thing to note, that A cross B equals the opposite of B cross A. We can do a couple of these little baby cakes. They're sort of fun to do. What would I cross J be? Well, notice, let me just draw the X, Y, Z axes. Here's the x-axis, here's the y-axis, here's the z-axis. Notice little I is pointing this way, J is pointing this way, and K is the unit vector pointing up in the positive direction. Bringing my hand here, if I move it from I to J, notice how's my thumb pointing? Up out of the paper. You see that? I cross J is going to be pointing up out of the paper. And also, what's the angle between I and J? 90, isn't it? So, and what's the magnitude of I? How long is I? 1. How long is J? 1. So if I wanted to talk about the magnitude of I cross J, it would be the magnitude of I times the magnitude of J times the sine of the angle, which is 90. Sine of 90 is 1, so this is 1 times 1 times 1, which is 1. So the length of I cross J is going to be 1. The length of these we could show the same way is 1. So what vector, if we go I cross J, and we can see it's going to be pointing up out of the paper in the positive z direction, what vector is pointing in the positive z direction but of magnitude 1? K. So I cross J is K. And how about if I go J cross K? It's going to be a unit vector. Which way is J cross K going to be pointing? If I take my hand and I move my palm from J to K and go perpendicular to it, how am I going? Positive I direction. How about if I go K cross I? Let's take my hand. Think of it here. I put my hand at K, I move it towards I, and how's it going? Perpendicular. It's going to be going in the positive Y direction, which is J. Some instructors like to do this. I'd like to go I, J, K. Notice if you take I cross J, you get K. If you take K cross I, you get J. If you get J cross K, you get I. But now what if you went the other way? What if you go J cross I? If you go backwards, J cross I, you go in backwards, it's going to be minus K. Because notice here, if I try to do J cross I got to put my hand on the bottom. J cross I, and my thumb's going to be going down. If you don't have any intuition with this and you're like, Miss Strocko, forget the right-hand rule. I'm not doing the right-hand rule. I'm not doing well with this. If you wanted to do I cross J, you could say, remember, I is 1, 0, 0. J is 0, 1, 0. Take that cross product. You could go I, J, K, put the coordinates here and the coordinates here, and you could just do it out the wrong way. But I think it helps to do this because it's quick. It's quick and dirty. All right. No, I don't want to do that. I want to do something else. Let's look at this. This thing right here. This has a very important significance, and I'd like to touch base with it right now. Let me draw a picture. Before I do my picture, let's do this. What's the area of a rectangle? Duh, Mrs. Strocko, I think that's arithmetic. You have a length, you have a width. The area of a rectangle is length times width. We're all comfortable with that, right? Okay, let's do a parallelogram. What's a parallelogram? A parallelogram has the tops are parallel and the sides are parallel. Does anybody, so this is parallel to that, that's parallel. What's the formula for the area of parallelogram? Okay, a parallelogram has a base. From here to here, this is a base. And it has a height. And the height is the perpendicular that if you go to the top and you drop a perpendicular straight down to the bottom, this length is called height. Now, I think most of you would agree, if I took this little rectangle out right here, you'll see this little triangle right here? If I took a scissors and I cut it out, I could put it right here. Okay, so if I cut that out, I'd have that. What is this? I think the area of that's going to be the same as the area of this because we just took that little piece and moved it over there. That's a rectangle, isn't it? And the area of that rectangle is its length times its width, which is the base times the height. So the area of a parallelogram is its base times its height. Okay? The area of this parallelogram is its base times its height. So, what if I have vector A and vector B, and I look at those two vectors? Do you see that if I drew a vector parallel to A, same length as A, and parallel to B, I could make a parallelogram. Vector A and vector B, if you draw a line parallel to A and a line parallel to B, determines some parallelogram. Okay? What would the area of that parallelogram be? That area of the parallelogram, aha, we just said, the area of the parallelogram is its base times its height. So it's going to equal its base times its height. What's the length of my base? The length of my base is the magnitude of A. Now, what's my height? Ooh. What's the height? What was the height of the parallelogram? It was the perpendicular drawn from the top to the bottom, making a right angle. I could have drawn my height here. I could have drawn my height here, right? Because I think all of you would see this line segment and that line segment have the same length. So my height, I'm going to draw from here down to here. And I'll call that H for height. So I could have the length of A, which is my base, times my height. Well, now wait a second, people. If I knew this angle, if I knew the angle that A and B made, what would be the ratio of H over the magnitude of B? The opposite side over the length of this side. What would be H over the magnitude of B? If I look at this right triangle here. Well, let's see, that's the opposite side. This is the hypotenuse. Last time I looked, opposite over hypotenuse was what? Sine of the angle. Oh, so my height here is the length of B times the sine of the angle between them. So for height, I can put in length of B times the sine of the angle between them. Hey people, a few minutes ago, if I can find the sheet, the magnitude of A cross B was the length of A times the length of B times the sine of the angle. The area of this parallelogram is the length of A times the length of B times the sine of the angle. So what we have just proven is this. Since we know the magnitude of A cross B is the length of A times the length of B times the sine of the angle, we have just proven that the length of A cross B is the area of that parallelogram. So when you go A cross B, okay, maybe A's here. No, I'm going to put A here and B here, and the reason is if I go A cross B, my vector A cross B is a vector that's perpendicular to B and perpendicular to A. And in addition, if I found this little parallelogram determined by A and B and found its area, the length of A cross B is equal to the area of that parallelogram. That's pretty cool. Okay? So if I drew a vector A and I drew a vector B, and I draw a line parallel to this and parallel to that, and that's producing a parallelogram, the area of that parallelogram is equal to the magnitude of A cross B. So that's sort of something that A cross B is sort of cool for. So A cross B gives you a vector, but the magnitude of A cross B gives you the area of the parallelogram determined by A and B when you put them tail to tail. All right, now let's do a few exercises. Did that one. I'm on to exercise 9, page 856. And I know this isn't odd, but I decided it was so important I wanted to go over it with you. Now, notice there's a bunch of these, and we'll go through them. They say state whether each expression is meaningful. If not, explain why. If so, state whether it is a vector or a scalar. Now, remember, when you take A cross B, you get a vector. This is a vector, that's a vector. You cross them together, you get another vector. Notice, if you take A dot B, this needs to be a vector, this needs to be a vector. When you take their dot product, what do you get? You get something that's called a scalar. And what's a scalar? It's just an everyday number. Where a vector is going to be something with components, right? X, Y, Z components. It's an arrow pointing in some direction. Okay, B cross C, what is that? A vector. This is a vector. This is a vector. Does it make sense to take a vector and dot it with a vector? Yes, this is fine. It's meaningful. And if I take a vector and dot it with a vector, do I get a vector or do I get a scalar? When you take the dot product of two vectors, what do you get? You get a number. And the fancy word for a number is scalar. Because this is a vector, dot product of two vectors is a number. We all okay? We're all right? Because remember, when you take the dot product like 2, 3, 6, dot it with 1, 2, 1, what do you get? 1 times 2 is 2, plus 3 times 2 is 6, plus 6 times 1 is 6, which is 15, which is a what? A scalar. Let's look at the next one, B. And all we're asking is it meaningful? Okay. A cross B dot C. A is a vector, right? That's what A is. It's a vector. What's B dot C? When you take the dot product of two vectors, what do you get? A scalar, which is a number. Can I take the cross product of a vector and a number? That does not make sense. This is a vector. We take the cross product of a vector with another vector. This doesn't make sense. Not meaningful. Are you all with me? In order to take a cross product, you have to have a vector with a vector. Think about it. This could be 2, 3, 5. This is a scalar. It could be 62. When you're doing your cross product I, J, K, and you put 2, 3, 5 here, you just got a stinking 62. Where are you going to put it? You need 3 numbers there. Not going to work. To take a cross product, you have to have a vector with a vector, not a single number. Okay, does this make sense? Well, A is a vector, and we're crossing it with B cross C. What's B cross C? A vector. Can we cross a vector with a vector? Absolutely. And when we do cross a vector with a vector, what do we get? A vector. So our answer, if we did this calculation, we would have a vector. So it definitely is meaningful. It's not nonsense. Let's try another one. A dot B cross C. All right. C is a vector. But what's A dot B? When you take the dot product of two vectors, what do you get? A scalar. When you take a cross product, you need vector cross vector. I got a stinking number across the vector. Does this make sense? Not meaningful. All right, let's look at this one. A dot B cross, now this is cross product. This doesn't mean times, like 3 times 5. A dot B is a scalar. C dot D is a scalar. Cross product does not make sense unless you have vector cross vector. Not meaningful. You could be smart and say, well, Mrs. Strocko, this could be 3, that could be 5. You could take 3 times 5. No, no, no. We're not talking about that kind of cross. How about this one? Does this make sense? A cross B dot C cross D. Well, when you take A cross B, what do you have? A vector. When you take C cross D, what do you have? A vector. And when I take the top product of 2 vectors, does that make sense? What do I get? A scalar. I get a number. That's what scalar means. This is meaningful. Okay, so I just thought it'd be helpful to look over those. All right, let's look at this one. This is exercise 10 on page 856. It says, find U cross V and determine whether U cross V is directed into the page or out of the page, except whoever did this one forgot to put what the rest of the directions were on U cross V. So let me take my book, which is 856, and just copy the problems. Since we forgot to type the whole problem, we just have the directions. So number 10, I'll redraw the picture. In number 10, we have a vector going this way, and they say the magnitude of U is 5. And they have vector V going this way, and they have the magnitude of V is 10, and then they have the angle between them is 60 degrees. They want us to figure out the magnitude of U cross V, and they want us to figure out whether U cross V is directed into the page or out of the page. Well, first of all, I'm going to do the magnitude. Remember, magnitude of U, oops, I didn't write that down too well, so let me get another sheet of paper. Remember, the magnitude of U cross V is equal to the magnitude of U times the magnitude of V times the sine of the angle. So right here, magnitude of U is 5, magnitude of V was 10, and the angle is 60 degrees. Last time I looked, sine of 60 was root 3 over 2, so we have 50 times root 3 over 2, and I guess I can cancel 2 into 50, goes 25 times. So the length of my vector is going to be 25 root 3. And I chose to use this because they didn't give me any components. They just gave me length of U, length of V, and the angle between them. So it made much more sense to use this formula instead of the other one. Okay? Now, so we have the magnitude of U cross V we figured out was 25 root 3. Now to figure out which way, the vector is going to be perpendicular to U and V. It's perpendicular, so I know it's going to be pointing out of the page, or it could be going in the opposite direction into the page. So to figure out which way it's going, I'm going to use the right-hand rule. Well, notice I got to go from U to V with the palm of my hand. I can't do that, you with me, in a nice counterclockwise direction. So if I go U cross V, I'm going to have to put my palm here on U, underneath the page, which you can't see, you with me, to V. And if I go from U to V, how's my thumb pointing? Down. So how's it going to be going? Into the page. So U cross V is a vector that's going to be going into the page, and it's going to be 25 root 3 long. Not hard. Let's do another one. Next one I want to do is number 16. Find 2 unit vectors orthogonal to both ijk and 2I plus k. I want to find 2 vectors, unit vectors. What does unit vector mean? I want them of length 1. But I also want them to be orthogonal to both this vector I plus j plus k and the vector 2I plus k. Now notice I plus j plus k, you might prefer to write that as 1, 1, 1, and 2I plus k we would write as its x component is 2. What's its y component? Doesn't have a j, does it? So what's its j component? 0, and then its k is 1. How can I get a vector, not a unit vector? How can I get a vector that's orthogonal, perpendicular to two vectors? In this section, it's the cross product, right? That's what we're doing in this section. If I take the cross product of these two vectors, I will get a vector that's perpendicular to both of these, right? The cross product, and let's call this vector A and this vector B. When you take the cross product of two vectors, you're producing a vector that's perpendicular to both of those. So I want to take the cross product of 1, 1, 1 with 2, 0, 1. I want to take their cross product. So coming up here, to take their cross product, I'm going to go I, J, K, and put 1, 1, 1, 2, 0, 1. Okay, and this gives me I times. Let's eliminate the row and column that I's in. So we get 1 times 1, which is 1, minus 0 times 1, which is 0. Minus J times. Eliminate the row and column that J is in. And that gives me 1 times 1, which is 1, minus 2 times 1, which is 2. Plus K, let's eliminate the row and column that K is in. 1 times 0 is 0, minus 2 times 1, which is 2. So we end up with 1I. Now this is a minus 1, but with a minus in front, so plus J minus 2K. All right, so the vector 1, 1, negative 2 is orthogonal to 1, 1, 1 and 2, 0, 1. So I have just found a vector this vector is perpendicular to both of these vectors. Except, wait a second, I didn't answer the question completely, did I? I got a vector that it's orthogonal to both of these, but wait a minute, wait a minute, wait a minute. They want me to get 2, which I'll worry about in a second. Right now I just want to get one answer, thank you. But they want it to be a unit vector. Well, how can I get a vector? So I have these two vectors, and I have a vector that's perpendicular to it, but it's not a unit vector. How can I get a vector that is a unit vector that's perpendicular to both of those? Well, do you all agree? We have the proper direction. We have a vector that's perpendicular to those. All I have to do is get a vector that's longer or shorter so that its length is 1. How can I make that be a, are you all with me? Let me draw this here. You've got the one vector, you've got the other vector, and you have a vector that's perpendicular. So it's orthogonal to both of those. But it might be too long or too short. You want it in the same direction, but you want it of length 1. How can you find a vector in the same direction of this one, but of length 1? How do we do that? Do you remember? What do we do? You divide it by its length. Remember, if you have a vector, let's say we'll call it vector W. If you take vector W and you divide it by its length, this gives you a vector in the same direction as W, but what? How long is it? But of length 1. So what am I going to do? I'm going to take this vector, because this vector was perpendicular to the other two vectors, so it's the right direction but the wrong length. What is its length? Well, let's see. The length of this vector. Remember, if you have vector A1, A2, A3, how do you get the magnitude of that vector? Remember, it's a square root of the x component squared plus the y component squared plus the z component squared. So the length of this vector is going to be the square root of 1 squared plus 1 squared plus a negative 2 squared, which is 1 plus 1 plus 4, square root of 6. So if I take this vector 1, 1, negative 2, and divide it by square root of 6, I can write that as 1 over square root of 6 times 1, 1, negative 2. I have no problem with square root of 6 in the denominator. That's fine. All right, so that's 1, and you could also write it if you wanted to as 1 over root 6, comma 1 over root 6, comma negative 2 over root 6 is fine. Now, that's one vector that's perpendicular to those two, a unit vector. How can I get another one? Any suggestions? What if I go in the opposite direction? How can I get a vector that's in the opposite direction? What do? Multiply it by by a minus, right? If you multiply a vector by a minus, you get a vector in the opposite direction. So this is vector 1, and the other one would be minus that. And this would be 2 vectors of length 1 and perpendicular to both vectors. So it's plus or minus. And that's how you get your 2 unit vectors. So what did we do? To find, let's go back and look what the directions said. To find 2 unit vectors perpendicular to both of these, we took their cross product. That gave us a vector perpendicular. But then we divided it by its length. And by dividing it by its length, that's giving me a vector that's in the same direction, but of length 1. And then if you multiply it by a minus, you'll have it pointing in the opposite direction. It still will be perpendicular to both of those vectors, and it will be of length 1. Okay, let's do another one. Next one I want to look at. Aha, area of a parallelogram. I already did this one. Remember what we said? If you take A, the parallelogram that's produced by vector A and vector B, how could I figure out the area of that parallelogram? We did that a few minutes ago. What was the area of that parallelogram equal to? It was equal to the magnitude of A cross B. Because remember, that was equal to magnitude of A times magnitude of B times the sine of the angle between them. And if you take the sine of the angle between them here, A times the sine of theta gave you your height. So the magnitude of the cross product we derived a little while ago was equal to the area of that parallelogram. So we have on exercise 24 on page 856, find the area of a parallelogram with vertices -2, 1, 0, 4, 4, 2, and 2, -1. Now let me just take a second to draw this. Let's see here. Okay, we're going to go all the way to 4. 1, 2, 3, 4, 1, 2, 3, 4, -2, and the lowest we're going is -1. So we've got -2, 1, which is right here. B is 0, 4. C is 4, 2. 1, 2, 3, 4, 1, 2. And D is 2, -1. 2, -1. Okay, and here is your parallelogram. Okay, now let's let this be our A, and let's this be our B. So if this is vector A, let's get its x and its y components. Okay? So vector A goes from here to here. What's its x component? Remember, if you're going from -2, 1 to 0, 4, and you wanted to get your x component, what would you do? You take this, you take the final one minus the initial. So 0 minus a -2 is 2. And to get the y, you're going to go 4 minus 1 is 3. So that vector is 2, 3. To get vector B, this goes from here to here. Again, remember, you go final minus initial to get each of your components. So we're going to go 2 minus a -2, which is 4, and -1 minus 1, which is a -2. And that makes sense, because going from here to here, you're going over and then down. Over 4, down 2. Now we want to get the area of this parallelogram. Now notice my picture is just in x-y space. This is your x-axis, this is your y-axis. And what did we say a few minutes ago? We said if you have a vector in 3 dimensions, if you take A cross B, the magnitude of A cross B would give you the area of that parallelogram. So vector A right now I just have in 2D. But if I'm in 2D, what is vector A's? Right now it's just 2, 3. What is its z component? 0, right? Because it's in the xy plane, so it went up nothing. And vector B is 4, -2, but since he's in the xy plane, his z component is 0. And we just proved a little while ago that the magnitude of A cross B will give us the area of the parallelogram. That's determined by A and B. So let's figure out what A cross B is. To figure out A cross B, I'm going to go I, J, K, put A across the board, 2, 3, 0. Put B across the board, 4, -2, 0. And this is equal to I times, now let's see, eliminate, 0 minus 0 gives me 0. minus j times, let's see, eliminate j. Ooh, 0 minus 0 gives me 0. Plus k, and let's see, k is a negative 2 times a negative 2 is a negative 4, minus 4 times 3 is 12, so this is equal to minus 16k. Now notice that is a cross b. This is the vector that's 0, 0, 16. So what's the magnitude of a cross b? How long is it? Well, if it's in the direction of k and it's minus 16, it's 16 units long, isn't it? If you don't believe me, you can get its length by going square root of 0 squared plus 0 squared plus 16 squared, and you'll see you'll get 16. Because remember, what this says is it's the magnitude of a cross b is equal to the area of the parallelogram. The vector a cross b was minus 16k. How long is it? It's of length 16. Are we all comfortable that minus 16k is of length 16? Minus 16k, people, just notice. Here's x-axis, here's y-axis, here's z-axis. If you're drawing minus 16k, you're going to be going in the z direction minus 16 down. How long is it? It's 16 units long. Okay, so we found out the area of that parallelogram was 16. Okay, everybody okay? I don't really like that though. Let me just check this. We got negative 2, 1, and b was 0, 4, and that length was 0 minus 2 is negative 2, 4 minus 3 is 1. That's good. I like this one. This length right here is, yeah, we're fine. Negative 1 minus 1 is negative 2, and 2, yeah, that's fine. And we took our cross product, and 2, 3, 0, 4, negative 2, and we're fine. Okay, moving right along, let's do the next one. Let's look at find a vector orthogonal to the plane through the points 2, 1, 5, negative 1, 3, 4, and 3, 0, 6. Put a star by this one, because this is going to come up again in section 13.5. Look what I have here. I'm just going to draw these as 3 points. I've got a point 2, 1, 5 here, and maybe I have negative 1, 3, 4 here, and maybe I have 3, 0, 6 here. And we're going to call them P, Q, and R. Now, you know, I'm just assuming that the paper is going through the plane that these 3 points are in. But you could have, you know, your points here, 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 and here. You know, a point here, and a point here. 3 points in space. Now, notice 3 points, if you take 3 points in space, there's a plane that goes through those 3 points. You with me? There's a plane that goes through those 3 points. Those 3 points might be such that the plane's like here, or it might be like here. You with me? I mean, there's all different kinds of planes that go through those 3 points. But you've got your 3 points, and maybe I can draw them. Here's 2, 1, 5. Here's negative 1, 3, 4. And here's 3, 0, 6. And maybe the plane that goes through those 3 has to come at some angle. You with me? The plane that goes through those 3 points. Those of you that had a little bit of geometry know that 3 non-collinear points determine a plane. We want to come up with a vector that's perpendicular to the plane that goes through those 2 points. How can I do that? Very easily. Look what I can do. Here is a vector that goes from Q to P. That vector is in the plane. Here is a vector that goes from Q to R. That is a vector that's in the plane. Well, if I want to get a vector that's perpendicular to the plane that goes through those 3 points, if I want to get a vector that's perpendicular to this vector and this vector, how can I produce a vector that's perpendicular to 2 vectors? The cross product. Now, first of all, I got to get the components of this vector going from Q to P. That's pretty easy. Remember, we go final minus initial. So it's 2 minus a negative 1, which is 3. 1 minus 3, which is a negative 2. And 5 minus 4, which is 1. And here, 3 minus a negative 1 is 4. 0 minus 3 is a negative 3. And 6 minus 4 is 2. Okay, and so therefore, if we want to get a vector that's orthogonal to this vector and this vector, we're going to do the cross product. I, J, K. We're crossing it with 3, negative 2, 1, 3, negative 2, 1, and 4, negative 3, 2. 4, negative 3, 2. Before I do the cross product, I just want to make sure I subtract it correctly. So 2 minus a negative 1 is 3. 1 minus 3 is negative 1 minus 3 is negative 2. 5 minus 4 is 1. From here to here, 3 minus a negative 1 is 4. 0 minus 3 is negative 3. 6 minus 4 is 2. So we're fine. So this is going to equal I times, eliminate the column that I's in, so we have a negative 2 times 2, which is a negative 4, minus negative 3 times 1 is a negative 3. So we have negative 4 plus 3 minus I, minus j times, eliminate the column j's in, so we have 3 times 2 is 6, minus 4 times 1 is 4, so we have minus 2j plus k times 3 times a negative 3 is a negative 9, minus 4 times a negative 2 is plus 8, so we have minus k. So the vector minus 1, negative 2, minus 1 is perpendicular to the plane. And if you want to multiply it by a minus, this vector is in the opposite direction. It's also perpendicular to the plane. Okay, so the cross product of two vectors gives you a vector perpendicular to it. So there's there's multiple answers, but if you look in the back of the book, they have 1, 2, 1. And I had negative 1, negative 2, negative 1. Well, if you multiply a vector by a minus, you're producing a vector that's just in the opposite direction, but parallel. So the one vector's going this way to the plane, and the other one's going that way, and here's your plane coming across. Okay, a couple more, and then I think we can call it a day. Okay. Let me comment on one thing. I'm not going to do it, but in your homework, in fact, let me just take these two vectors that we just had. Suppose I have the point negative 1, 3, 4, 2, 1, 5, and let's take the point 3, 0, 6. We just had these. This one was called Q, this one was called P, this one was called R. Okay? Suppose I wanted to find the area of not the parallelogram, but of that triangle. Okay, let's just talk about that. What if I wanted to get the area of a triangle determined by 3 points in space? Now notice, we could call this vector A, and notice I just figured out a little while ago that this vector was 3, negative 2, 1. And this vector here is B, and we figured out that one going from here to here was 4, negative 3, 2. Okay, now recall, if I drew a line parallel to this vector, and if I drew a line parallel to this vector, the magnitude of A cross B gave me the area of the parallelogram, right? Right? Now, let me ask you something. What do you think the area of the triangle is going to be? Half, that's right, because you're taking the parallelogram and you're cutting it right in half, aren't you? So to get the area of the triangle, find your A cross B, find the magnitude of A cross B, and then just take 1/2 of it. So if you have two vectors and you want to find the area of the triangle determined by those two vectors, all you have to do is take 1/2 times the magnitude of that vector. Now, I chose these 3 points because a few minutes ago, we actually did the cross product of 3, negative 2, 1 and 4, negative 3, 2. I did that right here. And I got that vector, A cross B, I got A cross B to be the vector with components negative 1, negative 2, negative 1. So the magnitude of A cross B is equal to the square root of negative 1 squared, which is 1, plus negative 2 squared, which is 4, plus negative 1 squared is 4, is square root of 6. So the area of the triangle, since the magnitude of A cross B gave you the area of that whole parallelogram, the triangle is just 1/2 of it, it'll just be 1/2 times the square root of 6. Okay? All right, one more thing we need to do before we call it quits. You also could have 3 vectors, okay, that determine what's called a parallelepiped. What's a parallelepiped? A parallelepiped is a shoebox, but it could have gotten a little soggy, so it's a little bit skewed to the right. You with me? So here's my little, but see, my sides are vectors A, B, and C. Now, the formula, if you took geometry, the formula that they'll teach you in geometry is the area of a shoebox is the area of the base times the height. So you got to drop a perpendicular from the top. See, here's the top of the box, and you'll see that this is the top of the box. This is the bottom of the box. And if I drop a perpendicular from the top down, that's the height. The volume of this would be the area of its base times its height. Now, a few minutes ago, to figure out the area of this base is a parallelogram determined by vectors b and vector c. Do you all see that? So the area of that base is just the magnitude of b cross c. Do you see that? Also, do you remember that if you take b cross c, you get a vector that's perpendicular to b and c, right? So this is vector b cross c right here. Okay. Its length is equal to the area of that parallelogram determined by b and c. Now, to get this height, though, do you see I have a little right triangle here? If theta is the angle between a and b cross c, this height right here, because notice if this is my theta and here's my right angle, this side right here, this right here, the length of A is your hypotenuse. What's this side in that right triangle? Is it adjacent or opposite with respect to this angle? It's adjacent. And I think all of us remember that if you take your adjacent side over your hypotenuse, and my hypotenuse is the length of A, that is equal to the cosine of the angle. So wait a second. H, this height right here, is equal to the magnitude of A times the cosine of theta. So I said the volume of this parallelepiped is equal to the area of its base times its height. The area of its base was the magnitude of b cross c. The height is the magnitude of A times the cosine of theta. But remember, what's theta? Theta was the angle between A and b cross c. Do you all see that? That's what theta is. Well, remember, when you took the dot product of two vectors, it's the magnitude of the first one times the magnitude of the second times the cosine of the angle between them. But wait a second. Theta is the angle between A and b cross c. So this actually is the dot product of A with b cross c. Okay, so we just proved that. So if you have a parallelepiped with sides A, B, and C, if you want to find the volume of that box determined by those three, and will you put this on your cheat sheet? Absolutely. But I think it's sort of neat to see why it's true. The volume is the absolute value of the one vector dotted with the cross product of the other two. And it doesn't matter which two you take the cross product and then you just dot it with the third one. We could have made A and C be the base and B be the other side. Okay, so that's sort of a neat thing. So if you have a vector determined by, if you have a box, which is called a parallelepiped, determined by three vectors, the volume of that box is equal to the one vector dotted with the cross product of the other two. Definitely put that on your cheat sheet. Okay, so let's just look at one more problem, and then I think we can call it a day. Okay, find the volume of the parallelepiped with adjacent edges PQ, PR, and PS. So we're going to figure out, first of all, what is vector PQ? Vector PQ, notice, goes from P to Q. Whenever we take from one point to another, we have to do final minus initial. So it's 2 minus 0 is 2, 4 minus 1 is 3, and 5 minus 2 is 3. So that's vector PQ. Now let's get vector PR. PR goes from P to R. So it's negative 1 minus 0 is negative 1. 0 minus 1 is negative 1. 1 minus 2 is negative 2. Okay. And vector PS is going to be 6 minus 0 is 6. Negative 1 minus 1 is negative 2. 4 minus 2 is 2. All right. We can call this vector A, this vector B, and this vector C. So our volume we determined was the magnitude of A dotted with B cross C. So first of all, what we have to do is figure out what B cross C is. So to figure out B cross C, again, figure out B cross C. We're going to put I here, J here, K here, negative 1, negative 1, negative 2, 6, negative 2, 2. And we're going to take I times, eliminate the row and column that I's in, so we have negative 1 times 2 is negative 2 minus 4, which looks like it gives me a negative 6I. Minus J times, eliminate row and column that J's in, so we have a negative 2 minus a negative 12, which makes it plus 12. So this is 10, so it's minus 10J. Plus K, eliminate row and column that K's in, so I have negative 1 times negative 2 is 2, minus a negative 6 is plus 6, which gives me plus 8K. Okay, and I'm just going to check these again to make sure I have them right. That times that, negative 2 minus 4 is a negative 6. This one's going to be a negative 2 plus 12 is 10, so it's minus 10. And that one is 2 plus 6 gives me 8. And our formula that says it's A dotted with B cross C. This is B cross C, so we're going to take A, which is vector 2, 3, 3, and dot it with B cross C, which is this vector right here, negative 6, negative 10, and 8. And that gives us 2 times a negative 6 is a negative 12. 3 times negative 10 is a negative 30. 3 times 8 is 24. So we have a negative 32 plus 24, which is equal to what? Negative 8? A negative 8? Is that right? 2 times negative 6 is negative 12. 3 times 10 is negative 30. 3 times 8 is 24. So those, yeah, because that is a minus right here. So we have a a negative 42, right? Negative 12 and 30 is a negative 42. So that's what, 18? 18? Okay, which gives me a negative 18. And so since it's the magnitude of those, it's the magnitude of A dotted with B cross C. That gives me 18 cubic units. Okay, for your homework for next time, what I would like you to do is to read pages 850 to 856, and then on pages 856 to 857, I need you to do numbers 1, 3, 5, 11, 15, 17, 23, 25, 29, and 31. And also, those of you that are home, you do have your solutions manual, and that's very good. And those of you that are in the studio, too. If there are ones that are in the solutions manual that you don't really follow, and you don't think the solutions manual is very good, I would prefer those at home to email me, and those that are in class can just tell me. And I'd be more than happy to write those problems and actually post them on the Blackboard site. So let me know which ones, you know, that you don't think the explanation in the solutions manual is very good. Okay, very good. Nice working with you. This one was a bit more of a challenge than the other two. Good luck studying, and I'll talk to you next time.